Hello, everyone. It's Sean. Welcome back to Having Fun Repairs. About a year ago, maybe a little over a year ago, Kip Hakes published a series of videos on the grandstand FireFox F-7. This being I got an offshoot of it here. Tabletop gaming console, older technology, we'll just put it that way, which here in America was sold under the Radio Shack brand as Astro Thunder. Okay, so slightly different name, but otherwise still the same item. Okay. Now, in Kip Hakes' videos, he reached out to his watchers, the general public, and me being one of those who watches his videos. I'll put the link or something to these three in the description. But what he asked was for help, and he called this FireFox F-7 like a diode destroyer. I think across his videos, he was actually looking at diode S05, S06, 09, 10, 11, just to name a few, and trying to determine suitable subs to replace those. And in the second video, I made mention of what other people mentioned, measuring the voltage drop across the diode, but also said, it's also important to measure the voltage at the diode's junctions, and it will probably be behoove somebody to actually measure the current draw. Okay, so those three things we're going to actually explore in this video, going over some of the diodes that he was looking at replacing. I think he has selected up Zener diodes. I thought that they were like Schottky barrier type voltage regulator type diodes. And maybe we can determine what suitable subs could have been used in his FireFox F-7 by way of taking apart this Radio Shack Astro Thunder and doing our own analysis. So that's what this video is going to be about. And again, thank you for tuning in. If you're new to this channel, you're already here, please consider subscribing. And at the end of this video, if you like it, let me know by giving me a big thumbs up and leaving comments in the description. All that being said, start testing this and taking it apart. The American version, Radio Shack Astro Thunder, was actually released sometime in 1986. It was inspired by Galaga and featured a large vacuum fluorescent tube display, or VFD, Victor Foxtrot Delta, screen. The game was portable and powered by 4 C batteries, and that's the first thing that I am going to check with this device. There is no cover for my battery cells, as you can see here, but I believe I can see negative terminal to here. Should still be able to power it up with a power supply. Let's see, can I get underneath here just a tad bit? And we'll at least see if it powers on. So my power supply itself, a little benchtop power supply you can see here in the background. So 4 batteries in series would be, let's see, 6 volts. We'll bring up current a bit. I'm going to take this up to, we got power right around 3, 5. We'll draw on 0.3 amps. Really, that display is what's eating up most of that current. There we go. We'll draw on about 0.3 amp, 300 milliamps from my power supply at 6.2 volts. And if I bring this around, you can actually see that nice, incredibly pretty. Man, I love these old retro machines. So much better than staring at, it came undone. Staring at a cell phone or tablet screen, in my opinion. Kind of wondering if it's coming over both speakers. Let me turn my filters. Y'all can hear what I'm hearing. Okay, filters are off. Let's power this off. We'll power it back on. I've got the right speaker off. Let's see if we get some sound. I do get sound out of the left speaker, right speaker on, left speaker, or turned off, I guess, on off, left sound. Yeah, I'm not getting any sound out of the left. Oh, nope. I'm getting a different sound out of the left. Okay. So I think it's safe to say that one side carries the music and one is, you know, kind of like the tones you would get if you were to hit a target, or, you know, little files like that. So it is powering up. At this point, what I'm going to do is I am going to take it apart and we'll start exploring the board. Well, we got it disassembled. I didn't want to cover the entire disassembly because, well, you can go watch Kip Hakes videos for that. However, I will annotate, just as a precaution, if you're watching my videos and you haven't watched his, after removing the 6 screws on the bottom half of the clamshell, keep in mind there's a hidden screw underneath the joystick top. You'll have to pull back a couple layers of plastic, one being a black sticker, to be able to find this screw, and then you can unscrew from there. That will be the final part to remove the upper clamshell. All right. As far as what I'm seeing, I mean, other than the fact that mine is a bit dirty, it does work. It's got some Nasuko capacitors in there. Nasuko started developing capacitors, I want to say, around 80 years ago. However, these electrolytics, it's very possible that this has been recapped at some point. I'm not seeing any leaky caps or anything like that. But, you know, given that this is my first time looking at this console, I'll probably go through and recap it myself, just for the fact that, you know, I have peace of mind that it's going to have some longevity. All right, as far as the screen goes, there is a bit of bleed in the upper right-hand corner right there. Whether or not that is a glue or a burn-in, I'm not too sure, but it is there. There's nothing really I'm going to do about that. Here goes our voltage regulator. As mentioned, we have our 2 ICs. One probably storing probably random access memory or some kind of memory. Another one dealing with the program itself. Or maybe this drives the display. I don't know. I'd have to look it up and be able to tell you more. But other than that, you know, 2 speakers on the bottom. You see the right speaker, the one that we get the startup sound, and then I think that's the left speaker. That would be the one that's giving us our, you know, little VFX, I guess, if I could put it in that term. You know, whenever we get hit or we shoot something, I guess. I haven't really played the game. This is as far as I've gotten into touching it at this point. I've had this sitting with me for about a year, wanting to do a video based off of Kip Hakes' video, and I just haven't been able to get around to that. So sorry, Kip, if I told you about this. I can't remember. I'll shoot you an email, but we're finally here to it. Okay, so what I want to do is we're going to power it up. Well, actually, let's have a discussion about diodes real quick, okay? Let's talk about a diode. All right, so I'm going to kind of draw this one slightly backwards just to emphasize a point. And we'll do like this right here. Okay. This is the typical symbol for a diode within a circuit, okay? And a diode is going to have one junction being a positive junction, and one junction being a negative junction, P and N junction. On the positive side, we call that the anode, A-N-O-D-E. That's the positive side. This is our anode side sitting over here. Okay. And then we have our cathode, C-A-T-H-O-D-E. That's the negative side of our diode. We got that sitting here. Now, there's an easy way to remember what side is what. Okay. If I'm looking at the side with the top hat, I can always go, oh, look, I have a, what letter is this? A K. So that's my cathode side, this side over here. And then I can say, oh, what's my anode side? Well, if I was to orient it this way and look at the triangle, what letter am I basically making here? If I was to extend out these legs a little bit, I'm making an A. So that's my anode side. All right. And as far as orientation of the actual devices on the board itself, you have a little diode that's going to look something like this with some legs coming out, and then a bar coming over here, and that bar represents the, you guessed it, the cathode side. So that's how you orient diodes. We're going to make measurements at its P junction, its N junction. We're going to make a measurement across, and then I'm going to have to desolder, and we'll make a current measurement as well. All right, so let me get this thing powered up, and we can begin with that. Okay, I have to be very careful with my my mats in here. It is conductive, so I don't put boards directly on this. While they're under power, it will short things out. So I make sure it's elevated. This one's on its clamshell. We should be good. Okay, so I'm going to bring up high voltage here a bit. We'll go to 6 volts. And we have power up. Everything is good so far. All right, the first diode I actually want to check is going to be diode S11 here in the back. And so what I'm going to do is I am going to look for the one that has a bar that's on the right side. So that would be the cathode side. Okay. And I might need to zoom out just a smidge here on the camera so y'all can see the measurement. Let me overturn that light right there. And I'll bring this in closer. And can we get a light over top? There we go. All right, let's measure first the anode side to my diode sitting here. I'm just going to go off of the negative rail that I have right here. And I am going to measure this side, DC. We have negative 38.2 volts. Ooh, interesting. And let's measure the other side. Negative 33.4 volts. Let me actually write these things down. You can see that this is a pretty high voltage diode. It is oriented based upon the polarity of our DC voltage sitting here. And the polarity is actually inverse. So negative 38.3 volts on one side. S11. Negative 38.3 on the anode. And what is it on the cathode? Let's come across. We have negative 33.3.4. We'll call it 0.4. Negative 33.4 on the cathode. All right, so this is a voltage drop of, what do we have here? I'll just make this a 3 to get it easier in my head. So that's going to be 0. Let's see, 4, 5, 6, 7. So it'll be 5. So we got a 5-volt drop across that diode, essentially. And if I was to take my leads here and physically go from anode to cathode, we should see that 5-volt drop. And we do. We're getting, I realize my arm is kind of getting in the way there. There you go. Negative 4.8. So there goes our 5-volt drop across the cathode. Across the diode. All right. From this point, I am going to power it down and power down my power supply. And what I'll need to do is I will need to desolder one of the legs of this diode. Okay. And I'm going to solder a wire to the other side, and we're going to have to use my multimeter in a way to make a current measurement. Well, in all honesty, before I do any of that, what I'm actually going to do at this point is go ahead and measure the voltages across the rest of our diodes. Let me put this over here. We'll put this into DC. Let me power this on one more time. We need to look at S10, anode, cathode, and drop. S10, S09. Let's do, I'm not seeing S08. I do see S12. S12 and let's see, S05 and S06, and I'm going to measure these as well. So this is essentially the same process. For instance, if I put my negative lead to the negative rail, if I come in here and look at S10 at the cathode, we have negative 5.9, and at the anode, negative 1.7, negative 5.9, negative, what was that again? $1.7. So essentially it's looking like a 3-volt drop. Let's measure across to determine that. And 4.1 volts. All right, I got to do the same thing for all of the rest of these. Well, here's the data that I have gathered thus far. I got to turn down my headset volume because when I hear myself talk, it makes me talk slower. Here we go. All right, so I put everything in order. S05 at the anode, negative 38, at the cathode, negative 37, voltage drop of 0.7 volts. The marking on it is a red band, S06, negative 37 at the anode. I saw 0.1 volt drop in DC at its cathode, or at the voltage at the cathode, but a 12 volt drop across. And I was like, oh, 3.7 to 0.1, that doesn't make sense. However, at S06, okay, if we were to, let's look at DC first. I'll try to get this, there we go, out of the way right there. Okay, at the anode, 3.7 as mentioned. At the cathode, 0.1. Let's switch this to AC. Actually saying 7 volts AC at the cathode when can't measure DC at the anode. The voltage drop though comes to 3 volts across in AC. So for that one specifically, I have given it 2 ratings. Negative 37 volts DC at the anode, 0.1 DC cathode, 3 volts AC, 12 volt drop in DC, 3 volt drop in AC, a marking of R. Okay, for S09, negative 5.9 volts at the anode, 0.8 volts at the cathode with a voltage drop reading of 6, and the color bands green and yellow. S10, 5.9 volts anode, 1.7 volts cathode, 4.1 volt voltage drop, and the physical marking on the board and on the diode is 7.5 B3. Okay, these markings will come into play, and so will these, I believe. S11, we got negative 38 at anode, negative 33 at a cathode, the voltage drop of 5, and of course a marking of 5.1 B3. At S12, we have negative 9 at the anode, 0 at the cathode, 9 volt drop across anode to cathode, and a marking of 9.1 B3. Now, these markings, what they pertain to is how much voltage drop. This, 5.9 to 1.7 tells me we probably have a bad cap in here. That's why I'm probably got some leakage in there. But the rest of these values match up pretty much with that voltage drop we're getting. And then, of course, if you saw my comment on Kip Hakes' video, I believe that these red and green, yellow are old germanium type diodes. So we need to find an equivalent for them. However, before I start digging into equivalencies for these diodes, I'm going to make some other measurements. I'm going to check the current draw through the diodes. And in order to do that, I have to set up my multimeter a little bit differently. And that will allow me to thus be able to calculate the wattage, because we need to know if these are going to be quarter watt, half watt, 1 watt diodes, because they will, they got to meet a certain rating if they're going to dissipate heat, especially if you have a voltage drop across them. And, that's going to turn into heat, so we need that rating. Of course, this involves math, so we've got to figure out current. I'll show you how I'm going to do that next. Now, what I've done in order to prepare the board to make a current measurement is I have lifted one side of, we'll start here at S11, one side of the diode out of the PCB, and where the other side was soldered to, I ran a piece of wire through the board and soldered it to there. Okay. Now, I don't like holding leads when I'm doing current measurements, because I never want to be a part of the active circuit by mistake. And in order to measure current, you have to measure in series with the device. What we'll do is I'll take my multimeter. I'll take the positive lead out. That is going to go into the A side, typically indicating current, and I will throw my probe down into DC, and then the A side for amps. From this point, it really doesn't matter which way we arrange our leads, because current's going to be measured the same way no matter what. And I can actually demonstrate that for you here in a second. But I'm going to insert my leads into these gator clips just like that. Hopefully making good contact. I need to get some probes that actually just have clips on it. All right, now with that done, we will turn it on and we'll see how much current we are drawing through this part of the circuit. And right there, you see it is 10 milliamps. That's pretty much all we're drawing right there is 10 milliamp. Now I'm going to turn it off. And actually, I think I'm going to go over to, I think that would be milliamps as well. Yeah, let's go here. I can switch this. Millivolts DC, millivolts AC. Oh no, that's just millivolts. So I can't do, that's not an amperage measurement. Can't do that one. So we're going to write down S11 as 10 milliamps, 10 MA, lowercase m, uppercase A. And I've got to go through the remainder of these diodes and do this process over again. This is very time consuming, so no point in me trying to film this all for you. I think you get the general idea just by one demonstration right here. Well, it's taken me a while to kind of work my brain around some of the things. And one of these diodes I'm not 100% positive on, I'll put it that way. But we got a selection, and that's at least a good start. And the diodes I selected should not cause any premature failure. I hope. We'll find out. in any other part of the circuit, that is. Okay, S05 and S06. Again, they have the red band, and I think to myself that they're either germanium or Schottky, kind of vintage diodes. You look them up. They basically come to like a 1N4001. Okay. If you were looking, that'd be like a 50-volt diode at 1 amp. Of course, we got what, negative 38. When it's not, soldered to the board, you see negative 40 volts DC. 0.7 voltage drop. Well, let's see, as far as amps goes, we're talking about 12 amps DC, 41 amps in AC for both of those. Comes out to 480 milliwatts. And I think to myself, well, in all honesty, this could be a 50-volt diode somewhere between 100 milliamps to 1 amp. So it could be something like a 1N4001 if at 1 amp, or 1N4454 if, say, around 100 milliamps. I'll probably start off with a higher value, but order the lower one as well. Okay. S09, again, green and yellow are its bands. I think old vintage germanium or Schottky glass diode. If you were to look it up, it comes that value would come to 1N54 alpha, the modern equivalent being the 1N5400, 50 volt at 3 amp. And you look at our values here, and yeah, it's kind of, excessive, I would think, given that we only see a 6 volt drop across it. But what do I know? Maybe, 990 milliamps, 540 milliwatts. But what do I know? We'll get that. And then if I have to source a diode of a lower voltage, and still within the amperage range, as like it's very similar to, like, in my opinion, to like the diode designed to drop like 7 volts, to be honest. But yeah, you can see the voltage drop across S10 is a little less significant though. So maybe it is that, I'm not too sure. We'll get the 1N5400 and we'll try it out. It'll probably be one of the last ones I put in. Actually, these top three will probably be some of the last ones I put in. Just because of my uncertainty, but most definitely S09. But at least we got a selection now, and we know that we can't be less than, whatever voltage and whatever current we're measuring. And then, of course, barring how the data sheet shows up when doing your research, either the amp rating or the wattage rating for these through hole type diodes, axial type diodes, or whatever they're called. We can't be less than the minimum. Typically, when you're looking at wattage, you would want to double it. So if we are at 400 milliwatts, well, that's half a watt. So you'd probably get like a 1 watt diode. But, that's neither here nor there at this point, I guess. So S10, I'm digressing. Let's get back on subject. S10, okay, its marking was 7.5 BD. Okay, now I wrote on here a 7 Papa Delta 7.5, which is a Zener diode 7.5 regulator rated at 500 milliwatts. Well, we follow down. Yeah, I do believe this is a 7.5 regulator. Okay, that must be one of the reasons why 7.5 is in there. We can see that we have 1 milliamp, which comes out to 6 milliwatts based off of the values in our calculations. Power equals voltage times current. So I think that's what we're looking for S10. Of course, we solder everything in and blows up. We'll find out real quick it's not. But I feel like we're safe to put that one in. S11 5.1 B3 was annotated on it. Kind of like 7.5 B3. I think this is a ZPD 5.1. Okay, again, this is a Zener diode 5.1 regulator rated for 500 milliamps or milliwatts. Excuse me. With our voltage readings, we had what, 30 38, so negative 40 at the anode, if I'm pretty sure. A 5-volt drop, okay? So a 5-volt drop across it. Rating for 400 milliwatts, you know, I looked this up, it's 500 milliwatts, so we exceed there. And then if we were to actually pull up the data on it, well, I was going to show some data sheets, but it's obviously getting washed out. Anyways, last one we have is S12. Believe could be a ZPD 9.1 as another Zener diode. This one being a 9.1 regulator, and rated for 500 milliwatts, and we can see that's well within our tolerance here. So these are the items I'm going to get on order first, and we're going to test them out and see how it performs. Well, just as we started with S11 in our testing, we're going to do S11 for substitution as well. So here's what I've done. I've removed that diode. You can see it right here. Okay. And I've put in the replacement. I'll give you the part number we have right here. What is that? Z or Zulu, Papa Delta 5.1, which you see right here on the packaging. Little comparison. Well, if I was to put this in front of the camera, maybe you can see a size comparison there if it's focused in good enough. Yeah, the replacement is a touch smaller in length, but not by much. So we're going to do some initial testing. Now, something I did not do when I first started working on this was going to my handy dandy thermal camera to see how much heat was being dissipated as current flow was occurring through this diode, okay, with the old one. Now, I imagine if we have a replacement, there's too much current flow, it's going to get excessively hot and burn up. I don't suspect that's going to be an issue, but, you know, it's always good when you're playing this game of substitution to go back through and verify some things. So, as of right now, let's see, the replacement diode is over here on this side right here. Actually, probably what I should do is get this lead into here like this. Okay, so we got and I'll orient this around. Okay. And there we go. That should be on there good enough. And then I can focus with my thermal camera on this diode right here. See if it gets hot. But the first thing we need to do is we need to make a current measurement. Again, I have my leads on my digital multimeter between common or ground and our 10 amp fused input for making a current measurement. I have this down into current for DC. Positive lead is going to one side of my diode. Negative lead would be going to the point in which the other lead of the diode would be soldered into the board. Here, we can probably get just a smidge closer, can't we? There we go. All right, so now I need to power it up, and let's see if we have, oh, there we go, 10 milliamps, essentially, and we got a working display, which prior S11, 10 milliamps. How hot is this diode getting? We're at 83, 82, 80 degrees Fahrenheit, which is not too hot. 70. we're getting into calibration. Yeah, hanging around 70 or 80 degrees Fahrenheit. And we jumped up to about 90. We're backing back down to 80. Down to 70. Yeah, I don't think this is going to be any issue. I'm going to let this run for a few minutes, see if we get over, see how hot this might get, and I'll come back and let you know. All right, so I've spent some time just letting this thing operate. Our main power supply is set to 6 volts. Right now we're drawing 0.298 about 300 milliamps from the power supply. Looking over the data for this ZPD 5.1 or Z or Zulu Papa Delta 5.1 diode, the operating junction temperature is what I'm going to specifically pay attention to for this kind of half watt 500 milliwatt diode is -50 to positive 175 degrees Celsius, which of course in Fahrenheit that would be, well, I'm not doing any form of math in my head, I'm just using an app for it. 175 degrees Celsius is 345 degrees Fahrenheit. So we're well within the operating temperature there. So at this point, I would say as far as amperage goes, how much current is flowing through the junction of this diode, I think we're pretty safe there. I need to get the diode now soldered into the board. Okay. And we're going to check the drop voltage, the voltage drop across it should still be what, about 5 volts. So that would be the difference between what we can measure on the anode. Previously it was -38 volts DC, and then at the cathode -33. So 5 volt. Yeah, 5 volt difference there. So that's going back to our little data sheet here that we made earlier as we were selecting what type of diodes to get. Again, this is everything I do when it goes into, you know, I don't always put those on camera. I take a educated guess at when finding a suitable substitute, and then I go through and I test these things after I put them in. Like I said, I don't always do this on camera, but this is how I go about this. Okay, and now I have the diode in, and I have swapped back over the leads on my multimeter here at the bottom. So we can now make a DC measurement, and I'm coming through. Let's take a look. Neg 33. Neg 38. Yes, so we still have our 5 volt drop there. That's no issue between the neg 38 at the anode and neg 33 at the cathode. So temperature is still good. And we jumped up to about 102. Then we back off to about 97. A little warm, but not over the rating that's given on the data sheet for it. Okay, so I think we've got S11 figured out here. Let's move on to a different one. Just for the sake of continuity, I went ahead and put back in the old 5.1 diode, and you can see here 92, 90. Barring what's going on the physical display itself, between 80 to upper 90s. So it's definitely well within the temperature range with the replacement diode into there. So I did want to cover that because I have a feeling that somebody's going to say something in the comments, and it's going to annoy me. So I'll go ahead and stick it in there. So there you go. You got the full complete on that one. Let's move on to another one. Another diode. Okay. Now we've done S11, we'll do S12. S12 was a 9.1 volt regulator. Okay. Let's see, we had -9 on the anode, 0 on the cathode. Looks like we had a voltage drop of 9 volts going across the entire diode, drawing about 1 milliamp. It was very low current. Here's the part number, Zulu Papa Delta 9.1. I don't know if that's coming through clear enough. There we go. And I've got a feeling that if the last one worked well, this one will be just as fine. So power supply on, turning up the DC supply to this, 6 volts. And we're back to making a current measurement. Let's turn it on. It's not powering up. Let me make sure I have nothing shorted out here. Let me make sure I get good continuity all across here. And unfortunately, it's not turning on this go. Well, I mean, it is turning on, but I'm not getting display. Again, 6.1 volts from the supply, drawing 0.2 milliamps. And this is saying that I've got 1 amp of current coming through here. But it is very possible that I don't have this attached good enough. Let me try to work on this for a second. You know, it really could just be that my leads are too much of a load for this. So what I'm going to do at this point, we saw the current measurement. I'm going to tack these leads back together with a bit of solder, and we'll just go through and do a voltage measurement, see if it will power up. All right, I've tacked the leads back on, and as suspected, now it's actually powering up the way it should. So we made a current measurement. Let's make a DC measurement on this now. Switch this over to volt DC. Come through and check our leads. Of course, it should be 9 on one side and 0 on the other. There we go, 9 volt, 0. So we do have a full 9 volt voltage drop across it. And so long as it doesn't heat up, we should still be good here. Where are we at? That's looking at the IC. Yeah. That diode is not heating up. Any substantial amount of heat is not coming off of it. So again, and we're still drawing the same from the power supply with this. So 6 volts, about 300 milliamps, 0.3 amps, so 300 milliamps. So not drawing too much current. We'll say that Zulu Papa Delta 9.1 is a suitable substitute for S12. Let's move on to the next diode. Well, I've taken out the 7.1 diode regulator. That would be S10, which we measured -5.9 at the anode, -1.7 at the cathode. It had a 4.1 voltage drop across it. Current measurement was 1 milliamp, so I'm slightly concerned if it's going to power up if I'm taking my multimeters to leads, put it into current, and trying to do a current measurement. But that being said, so I'm going to forego a current measurement on this one, and I think I can anyways. Let's consider it this way. What is Kirchhoff's current law state? If you've watched my DC training videos, you have heard me use that term before. Well, the total current entering a junction in an electrical circuit must equal the total current leaving the junction. So if I power this up, if I see, let's see, 6 volts, around 0.3 amps or 300 milliamps coming from my supply over there. Somewhere between 280 to 300. I think I'm going to be just fine. But if it skyrockets, if it's substantially higher than that, then I know that this is not the proper diode for this circuit here, and hopefully nothing blows. So here's what we're going to do. Let's turn on the DC power supply. Okay, I'm going to take myself back up to 6 volts here, almost at 6 volts, 5 and 6 point, a little bit too much, 6.13 volts right there. Let's turn it on. It is powering up. Okay. 0.29.3 amps. So between 280 and 300 milliamps. Let's do our DC measurement. And let's see, what do we got here? 1.7. 1.7. Yeah, a little bit weird. Let's see what we get across. Yeah, still around the same thing. 4.3 versus 4.1. We're pretty close. But this does seem to be pretty happy in circuit. I think I'll take a my Klein tool and just make sure that it's not overheating yet again. Let's see. Touching the diode right there, and yeah, it is not heating up at all, and my display is working. So yeah, a little bit of a higher current draw. It's averaging more around 0.3 this go around. But yeah, still not very substantial difference there. So again, at the cathode, we were measuring what, 1.7. So that's very close to what we originally had at 1.7, and then negative 6.1 is what we're getting now versus 5.9. That's very close, but we're still, approximately at that, 4.3, 4.1. It's jumping there. But we're pretty much there. We'll say that's a good substitute for that part of the circuit. Now we're going to move on to, I think, what would be considered the harder ones to substitute. S05, S06, and S09. Well, let's talk about S05 and S06 for a brief second. I've already pulled out S06. We'll be testing this one first, okay? But the way these diodes are arranged on this PCB, can we zoom in for a second? Okay, I'll bring this up with S05 anode to cathode there, S06 anode to cathode there. This actually would be arranged that way around. Okay, I believe this is a rectifier. I believe this is a full wave rectifier of sorts. Not a full wave bridge because you'd need 4 diodes, but I do believe this is a rectifier circuit. Okay, so if I didn't, I'm pretty sure I mentioned this. I'm choosing between either 1N4454. Okay, probably should zoom back out here. Let's zoom back out. There we go. 1N4454. You can see that part number right there. 75 volt, 200 milliamp rectifier diode. And I also grabbed a 1N 4001. Here we go. This is a 50 volt, right? 1 amp rectifier diode. We're going to try the 1N4454 first. This is where things can probably get a bit squirrely. and check it out. And I'm back to doing a current measurement first. Again, yeah, let's see what happens. Turn on the power supply. And let's see what happens. Again, this was 1N4454. That is what we're using first. This diode, there is definitely a difference physically. Here goes the one that I removed. Okay. And you can see the one that I put in right there. Definitely a physical difference between these two diodes in both size and, color, because of the, what's marked in the cathode. Anyways, let's power it up. No power. Oh, that's right. I have my 6 volts turned down. Heart dropped for a second. I was like, oh, I've broken this thing. I've broken it badly. Because this is a rectifier, both of them probably need to be swapped out with the same type of diodes. But we'll see how it behaves. Okay, 6.12 volts DC powering on. And yeah, powers up. We're at, 10 milliamps. So I believe it was 12 before on DC, and then we had an AC side, right? Don't really remember. Anyways, we're drawing by Kirchhoff's law. It looks like we're looking good from the main supply. I'm drawing 0.2, 0.3, which is no different from before. Okay. So, let me get my thermal imager to it. And if we're not getting too hot, actually, I'll tell you what, we'll do a voltage check next and then take the thermal imager to it. So power supply off. Let me come back once I got this soldered in. So what I've went ahead and done is replace both S05 and S06. I've got them quite a bit lifted off the board there. Okay, we're going to go ahead and make AC/DC measurements. Let's power it on. And I'll probably just stick with the DC side. It is powering up just fine. Let's look at S06. Yeah, 0.1, whatever. Neg 38 on the other side, on the anode. It's neg 37. Previously, let's look at the cathode of S05. Neg 38. And we'll look at the anode. Neg 38. All right, so how much of a voltage drop do we have over S05? .08 and 16 volt drop across here. I think it was a 12 volt drop previously. Let's see if we have elevated voltages at our other diodes. Let's look at S12. Well, actually, let me go to S11. And neg 38 at S11. But that's around the same. Let me check here. S10. Neg 5.9. That's not elevated. Let me check S12. That was 9 volts. So that's not elevated either. I'm not seeing really any elevated voltages. And, even though we're slightly different here, it's not substantially different. I'm not drawing any more current from the main supply. 6.17 volts DC. Currently drawing 280 milliamps or 0.280 amps, and it's jumping between 280 290. Let's look and see if we got any excessive heat coming off of them. Otherwise, I'm going to say that 1N4454 75 volt 200 milliamp rectifier is perfectly fine as a sub inside of here. And yeah, no, so that heat spot you're kind of seeing is being washed out a bit by my upper camera. That's coming from this S09 diode, which was hot previously. But yeah, I'm not seeing excessive heat across these diodes. Put my little wooden dowel behind it so I can isolate it from the background. But yeah, no, we're good. This is working fine in my opinion. And I think, again, we've hit another good substitute. I'm not even going to bother with the 1N4001 diode 50 volt 1 amp. That is a much bigger diode than ones that we just put in. Size difference. It would work as well. We don't have elevated voltages. Regulator still seems to be working just fine. You can see the size difference in the 50 volt 1 amp. Obviously, it would be bigger to hold be able to dissipate heat better, in how the silicon's used. Much higher amperage, much more heat dissipation. Those kinds of things that go into engineering, which is not really what this discussion is about. It's about finding substitutes, suitable substitutes for this game. So that's going to leave S09 left. Well, let's work on S09. All right, let's talk about S09. Okay. When I was making measurements before, across anode, I was seeing negative 5.9 volts. And the cathode, 0.8 volts, we saw a 6 volt drop. Measured 90 milliamps. And this was slightly over a half watt diode. Okay. And for the life of me, I don't know why I did this. I went against my better judgment in the selection and decided to go with a 1N5400, okay, which is a 3 amp diode, okay, which is way overkill. Now, I don't have that diode in. Let me explain why in a second. Here goes S09 removed. You can see how small it is on camera there. Okay. And here goes a 1N5400 3 amp Schottky diode, rectifier diode. Okay, yeah, that is so substantially bigger. As a matter of fact, there is no way that the leads off this diode are going to fit through that PCB. So what I've done is I've opted to put in one of the diodes that I selected for S05 S06, and the one that we ended up not using, the 1N4001 50 volt 1 amp diode. Okay, so that should have enough overhead, I think, there. We're not drawing a whole lot of amperage, but yeah, I think this diode was around like a watt or so. So I think we'll be okay to use that one. Let me verify it real quick. Yeah, that should most definitely be more than okay. But my main concern is are we going to have too elevated voltages? I don't know. We'll see how this behaves in circuit. I think it's possible that you could probably get away with using what was it, 1N4454 that we use for S05 and S09 here in S05 S06 here in S09, but we'll see. Anyways, so we're going to make a current measurement first. I've set up my multimeter for current measurement. Power supply 6.17 volts DC. Let's turn this on, and we are powering up. Now we are at an elevated current, so that is not good. 300 to 0.4, 450, 450 milliamps. So this will definitely drain a battery a lot quicker. Our amperage through from the diode over in this circuit, and keep in mind, we're still seeing what point or 90 milliamps, so that's not too shabby. Yeah, this is definitely not the right selection per se, because we are at an elevated voltage, but it is currently working. I think I'm going to solder it in and just make some other measurements, and maybe we can go with a different one. But as it stands right now, actually, let me see, is there anything getting too hot? Let me check some heat signatures on here. Give me a second. No, if I power this up, if we check the diode, we definitely have elevated heat coming through it as well. 130 degrees Fahrenheit versus around the 90 we were seeing before. The rectifier we have down here, 3-pin transistor, it's in about 120, so I think that's kind of elevated too. So I don't like how that is in circuit. We're going to have to find something else. All right, so here's what I've done. I've put kind of our previous diode that we removed, the one that originally came in S09, in parallel with the 1N4454 that we use for S05 and S06, because we're going to test them both. You can see I've got them split in between, so current's going to be allowed through the path of least resistance. So right now, this diode is not really connected in circuit, because you can see that it is, the other side of the diode is not a part of the circuit. So we're looking at amps, and we're at, 80, 90 milliamps DC. I'm using my, zoom out a bit, my Klein tool device here, thermal device, to measure the temperature. That diode is ranging between once it runs to its calibration, 102. It seems to get anywhere between like upper 80s to a little over 100 degrees Fahrenheit, 102. Mostly in the 90s here. Okay, now I want to take a look at this 3-pin rectifier we have back that way as well. Just kind of monitor it. About 89. Let it calibrate. 92, 96, 95, 96 degrees Fahrenheit. All right, so as far as current draw goes, we've got a good basis. Let me turn this off. All right, here's what we're going to do. I'm going to take my multimeter off of that old diode. Okay. And I'm going to put it onto this 1N4454, 75 volt about 200 milliamps, and we're not seeing those elevated voltages across this, basically a rectifier. So I'm going to come back through. We're going to power up. Hopefully we are back down to somewhere around 300 milliamps at the supply, and hopefully we're still maintaining about 90 milliamps through this diode, and we don't have elevated temperatures either. So let's power it up. It is powering up. Maybe slightly higher on the current draw there, but again, you know, averaging between 80 and 90, so 85 milliamps to about 92, I think I'm seeing. All right, a power supply definitely does look better. I'm at 0.3 amps or 300 milliamps, so we're not at that elevated 450 milliamps. Let's check our temperatures here. About 102, 109, slightly elevated temperature. 106, 98, 104. But that's not too high. It's not 130, 140. And again, 102, 140, you'd expect that with that diode allowing more current. See, 107. So that's slightly elevated, but I'm not too concerned about that, especially because we're not drawing as much current as what we were seeing before. So looking over now at the 3-pin voltage regulator, whatever we have there, 93 volts Fahrenheit, maybe slightly elevated 92, 93, but that's really no concern there either. I wonder what happens if we can get out demo mode. Remember, select and start. There we go. All right, now we got the game going. See that we're consistently sitting about right there. Almost 0.1 amp. Yeah, you're not getting all the sound effects that I'm getting. Thankfully, my filters are cutting most of that out. But yeah, I'm not seeing a significant issue there whatsoever. So I think it's safe to say that you can use 1N4454 for all three, S05, S06, and S09. Let me finish getting that soldered in. We'll do a voltage check across just to, you know, final analysis on this. The last thing we're going to do here, as I said, is a DC measurement. So I've got my multimeter set up with the leads in the right spot again so we can perform DC measurements. All right, let's turn this on and let's see what voltages we're getting across from here. So I think previously S09, what was it? 0.8 and then 6 volts. Oh, 6 volts was a drop. So negative 5.9 and 0.8. Let's see, what are we getting? 0.8. There we go. Or 0.08. Maybe I had a 0 there. 6 volts right there. Okay. What were you seeing across this? Yeah, we're seeing a 6 volt drop. So yeah, it's acting as another rectifier right there. I think you can get by with using this one for there. So what does this tell us as far as our analysis here? Well, let's discuss this for a second. Okay. It tells us that well, can I kill some lights here? Will this make some things better? Give me a second. This is my window over there that's washing things out. Here we go. Window shut, so not as much ambient light washing things out. Let's talk about what we have here. So first off, with 3 diodes, the indicator on the board was mostly our context clue there. Those were Zener diode regulators, I guess you could say. The voltage drop across them being very important. 9.1, 5.1, 7.5. Okay, so that got us into the right direction for S10, S11, and S12. Okay. Then from there, what we suspected to be germanium style diodes, not transistors, non-linear devices. Not linear just mean whatever's in. It's not linear coming out. Anyways, S05 S06 got us thinking about 1N4454 and 1N4001. Of course, we were looking at checking how much current was being drawn, the voltage across, and the max we were seeing was 37, 38 volts, and of course these were 50-volt diodes. So, and we went with the 1N4454 75 200 milliamp rectifier. Description VR is 75 200 milliamp, which did not exceed anything that we were seeing over here as far as current draw and stuff, and had no significant effect on our overall system or device. And then obviously what we initially selected, being way too big, 5400, that did not, even though you researched the green yellow germanium transistor, that's kind of what it leads you to, is this 50-volt 3-amp, which is just way too massive. So we substituted that down to the 1N4001, which was the 50-volt 1-amp, and then we went with the 1N4454 in S09, and then our current draw from the power supply was still around 300 milliamps. That dropped down there. Voltage drop across the diode was fine. So things started looking good. So I would say, it's about half and half when you're trying to determine a suitable substitute. Yes, indicators can get you to a specific point in selecting a diode, but you also do need to take a look at current, and you're going to look at the voltage either at the anode and cathode, or cathode and the cathode, or cathode, and you can check the voltage drop across, because those are all things that I need to verify, even if the nomenclature is perfect, right? What's stamped on the device gets me to the right thing. I still want to check those things after. So it's a little bit of a hand in hand there. Now, do I believe that 1N4454 should be the one that we absolutely use for S09? Well, the circuit is functioning. I'm not 100% positive that the type of diode that's being used in S09, but we were able to play the game, and the voltages weren't too far elevated, and our current wasn't significantly elevated either, with 1N4454 put in S09. So I think we would be okay long term, even this little rectifier right here, to use that. So what does that mean? That means that as far as our substitutes go, for S05, S06, and S09, you are going to use a Mauser part number 512 TAC 1 November 4454. Okay. And then for S10, S11, and S12, that will be these part numbers right here. Zulu Papa Delta 7.5 or 5.1 or 9.1. And that will get you what you need as far as those diodes are concerned. So what am I going to do now? Well, I need to button this up, get the original diodes back in, and maybe we can just play for a second. this is definitely going to do it for this video. If you stuck along and you watched all this with me, please let me know if you enjoyed it by leaving a comment, giving this video a thumbs up. If you're new to this channel, please consider subscribing. You're already here. Why not? You know, that's the principle of how channels grow, right? All I can do is thank you for your time and thank you for watching. Hopefully this has helped out other people working on a Radio Shack, older Radio Shack toy like this. Hopefully Kip Hakes, I'll probably be reaching out to you if I haven't already. Hopefully you've this has helped you. If you go back and look back at your previous content, this, you know, again, these are the things that repair technicians, electronic technicians, these are the kind of things that you need to consider when you want to substitute out a device. Okay, and now I'm kind of glad that things happened the way they did with me choosing the wrong diode and then having to mention Kirchhoff's current law and the fact that our power supply at that one instance was drawing more current than it was with the previous diode. So it was a good opportunity to show all those different things that you need to check for. You need to test the anode, voltage at the anode, voltage at the cathode, your voltage drop across the diode. You need to test current draw. Yes, you know, indicators and stamps, it can get you a little ways as far as substitute selection goes, but there are definitely other things that you should consider as well. Okay, but that's going to do it for this video, or in the words of Kip Hakes, it is game over. Take care.